good. Um, so, welcome to the most wonderful class you'll have on a Tuesday morning at 8 a.m. or Thursday morning or Friday afternoon at 1 if that is possible. I know most people in the room. For those who don't know me, hi, I'm brother Marius. I'm a total nerd. Also, in a weird twist of fate, most of the work that I've done has been in aerospace engineering. So if you ever want to talk airplanes, I'm kind of really happy to do that. But it also means that if you have anything from either environmental or petroleum engineering topics that you're interested in looking into, please let me know about them. I'll be putting up a Google sheet in the next day or so, so you can get those ideas to me in an anonymous manner if you want to do that. But it's stuff that I might not be familiar with, and you guys might be more so than I. So please let me know if you have any ideas or things you'd like to look at, situations that you want to expand on, stuff like that. As far as this class goes, one thing that is already weird is that I'm wearing a microphone. For those who weren't here about 10 minutes ago, Desmond is also taking this class while he's in France. So I'm recording the lectures for him. For you guys, that means that all these lectures will be up on YouTube if you want to go back and review anything. So pro for you guys. As far as details about this class, you all have taken or have gone through statics, maybe even call it dynamics. So in those classes, you talk about forces acting on objects. You got to the point where you could break down forces acting on individual members, distributions of forces inside of members, all that kind of stuff. What we're going to do is we're going to take those forces and make that number mean something more, because the structure isn't static. Yes, your teachers lied to you. Nothing stays still. Everything bends, and that big question we want to ask here is, will it break, or how far will it bend? All that kind of good stuff. So more so, what are the loads going to be, but can the structure take the loads, and how big does the structure have to be in order to take the loads? That's kind of what we're going after here. So it's an application. It's going to be an interesting schedule. It's going to be an interesting schedule. It's going to be a jam-packed 2 lectures, who's Thursday and Tuesday. The recitation on Friday is optional, but very highly recommended, and I will most likely be using that for when we have tests, so that we can keep up with enough time for reviews as well as for getting material in. As far as where I am, if you had me last semester, I no longer live in that hallway. I'm back in the corner. If you know where Dr. Labar lives, Dr. Chin, I'm back in that annex, if you will, back in the corner by what's called the Energy Institute. Office hours are 9 to 10 all week. At least that's kind of what I sketched out. Does that work for everyone? Yes? Yes? Okay, cool. Great, then that's that. Feel free to stop by then or any time, really. Just that's the time that I'm guaranteed to be in my office. If you stop by another time, I might be there, but but I'll be happy to answer a question at any time. Other than that, assignments. I really tried hard to find a final project for you guys. Unfortunately, we don't quite have the equipment to do it yet. So I'm sorry. We're going to have a regular final exam. But that's kind of what I'm looking at. In terms of homework policy, I really like just moving forward with stuff. And I've learned that what I was doing last semester wasn't doing that. So here, I'm looking for homework by the beginning of the class. That's 8 a.m. 1 week after it's assigned. If you can't get it in by then, just let me know. We can work work something out, but I'd like to know well in advance. So just give me a heads up, and we work something out. Are there any questions? Sweet. Then onwards and upwards. So cranes. Well, we're going to start with cranes. So you're going to see this diagram a lot in the next week. If you have some paper, pull it out, because this is we're going to start with a quick static analysis of this, and move, let's call it, and then we're going to start throwing stresses and all that kind of jazz is at it. So if you want to sketch out this basic structure, you can imagine that these 2 points here are both pin joints, and hopefully this marker keeps on working the way that I wanted to. Oh yeah, this is a pin joint too. So all joints are pinned. Ignore the gray thing. It's just kind of there. We have an arm here. And if my sleeve didn't hit it, it'd be even better. We have an arm here that's supporting some load. That, if you looked at the next slide, we're going to find out about. And that arm is being supported by a hydraulic ram. Cool. Just going to flip the next one, because it has a bunch of, let's call it, dimensions on it. So here's the deal. And actually, you know what? In order to make life a little bit more straightforward, we're going to ignore this and just add it onto the weight of the arm itself. So it's a 11,900 pounds support arm. Turns out that cranes are really stinking heavy, heavy. And that arm, so the length of this is 36 feet. Got that already in there. Yeah. That should be all the information that you need at present. So just let me know when you're done writing that down, because the next thing we're going to do is solve for all the forces acting on this. All right. Almost there? Okay. So in theory, this should be something relatively familiar, right? It's just a statics problem, essentially. The reference frame might be a little weird because it's not had a cantilever, rather it's an arm cantilevered from a different direction than normal, but should be able to figure it out. So before we get too far into solving this thing, how would we go about solving this thing? Anyone? What would be kind of like your first thoughts towards this? I know it's 8 or 9, but we can do statics at 8 or 9. Free body diagram, I love it. Free body diagram is always the right answer. So, what would I draw a free body diagram of? Okay, so like I'd have something like this. So that's a really weirdly shaped arm. Hang on. Let's see if I can at least draw a straight line. Okay, so this is the arm, say. Wow, that's a new one. Cool. So this is the arm, say. Okay, so what would I pay? So what's poking at this arm and where?
The center mass of the cell.
Okay, okay. So around here-ish, I have something like force due to gravity. All right, and you said that's in the middle. The length of this thing, is 36 feet. So this is about 18 feet. All right, what else?
Hydraulic arm. There's a ram in the middle.
Okay, well, it's not in the middle.
17.3 feet.
Very, very good. So it's about there. This is 17.3. I probably need to get a couple more rubber bands for next time. 17.3 feet from the top. We have hydraulic ram pushing in. Do we know the direction of that?
20. I don't know.
Okay. Let's look at that hydraulic ram. What are the boundary conditions on it? Okay, so it's angled 20 degrees from the vertical. But what's holding it at each end? Is it fixed? Is it like rollers? Is it a bearing? Is it pinned? Is it? It's actually pinned. It's actually pinned. Yeah, yeah. So can those pins resist moments? Can pins resist moments? The answer is no, right? So if I have let me give myself a little bit more space here. So this is force due to gravity. So if I have my hydraulic ram here, and it's pinned on each end, those pins cannot resist any moments. Can this guy, can the force generated from this pin or this pin generate any moments on this? If there are no moments acting on the hydraulic ram, can the forces create any moments? Does that question make sense? Yes? No? What? Okay. How does it and how does it not?
Like, is it a moment on the hydraulic ram or like a moment on the entire system? Just like anywhere.
I see what you're saying. A moment just on the hydraulic ram. You know what? We'll come back to that quick question. We can answer that later. That might be more evident. So, like Ian said, we have the hydraulic ram poking right here at 17.3 feet from the top. We're going to just say it's acting at the center of the crane pin arm because it makes it easier. And pins can react forces. So there's force ram Y and force ram X. Sound good? Because pins react to forces. No moments. Are there any other forces poking at the arm? The counterweight. So the thing dangling from the end, right? Okay. So it's going to be acting on the end. It's going to be acting straight down. Correct? Cut. What else? If anything. Pin at the bottom. Correct. So again, we have two reaction forces from that. Okay. Is there anything else? check your sketch, because I don't have it up there. Plus, any other forces acting on this?
Do you want to add the 10 of the ram?
That's this guy.
And the earthquake.
Oh, yeah, which called, right now we're just doing the free body diagram of the arm. Yeah, so this is just the arm. Anything else? Okay, cool. So we got one force that we know, right? Because we know this, which called this guy is like 11,000 pounds, something like that, or 20,000 pounds.
11,900.
Say again?
11,900.
The counterweight. Thank you. Okay, so we know this guy, and we know this guy. Although we should keep in mind that that 11,900 pounds is distributed across the arm. That won't make a difference for our static computation, but it will make a difference for the strength of materials. So one. Okay, so now we have two knowns, we have four unknowns, and we have a bunch of and we have a bunch of solving to do, right? But we have some tricks, right? Because we actually really only have a couple of unknowns. So if we look again, hope this works. So if we look again at, let's see if I can do this. Nope, it didn't. So if we look again at the full system, we have something like that, right? So we have the arm, we have the hydraulic ram, and we have this counterweight it's called dangling off of the end. We have a whole slew of pin joints, and it's holding it all together. And actually, sorry, I drew this sloping the wrong way. Should be going like that, right? Oh, and this all is at some angle. Some angle there that we'll fill in a minute. So this is this is what we got. We could try to do some statics both beforehand to find all these reactions here, right? But for now, we're going to skip that because because we can do some simplification to this structure. You guys remember two force members? So looking at this hydraulic ram here, at the top and at the bottom of the ram, it's pinned. So those pins don't exert any moments on the hydraulic ram, right? That means that there can be no moments acting on the hydraulic. If there aren't any concentrated moments acting on the hydraulic ram, these forces can't exert any moments on the hydraulic ram. Therefore, those reaction forces have to be pointing in what direction? If they're not going to create any moments about the ram, what direction do they have to be pointing? You guys did trust analysis, right? Remember that whole painful thing? So what direction could you assume for your two forces, for forces acting on your two force members? Okay, cool. We'll play with that. So if I have, just back up a second. So if I have a bar, this is just a generic bar, and I push on it at one end in some direction that's perpendicular to it, that'll create a moment on the bar, correct? Cool. All right. And so long as I have some component of force that's perpendicular to the bar, it'll create a moment around it, correct? Like even if I had my bar and I'm pushing from like this direction, I still have a component of force perpendicular to the bar, right? And that still creates a moment. So the only way that I'm not going to create a moment by pushing on this bar is by pushing parallel to it. So that's a example of if I have pin joints on this, which cannot resist which cannot resist a moment. If this bar is static, so it's not turning, it's not moving, the only way the only way to satisfy the boundary conditions, meaning the only way that there are no moments acting on this bar, is for the forces to be parallel to it. So if we go back to our hydraulic ram, so we have arm, ram, pin, 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 weight. The only way, it's called this bar here, it's pinned to both ends, so there are only forces acting on it. There are no moments that need to be resisted. Therefore, the force at each pin has to be directed along the bar. We equal with that? Bless you. Therefore, we can simplify this. Instead of having two reaction forces that we have that we know absolutely nothing about, really, there's only one. Rather, we can say that there's only one because we know its direction. And if we know direction, all we need is the magnitude of that reaction force. Does that make sense to everyone? Cool. All right. And we could kind of apply the same logic to the, actually, we could apply the same logic to the pin here, except for what? Is if I take moments around this point, are there moments acting on this arm? Is there a moment acting on this arm? Okay. Okay. What? Yes? The counterweight, right. This is pulling down on the arm in a way that is not perpendicular to it. So there is a moment here. We cannot just say this is a two-force member because it's not. We have a force here. We have a force here making a moment. We have a force here making a moment. Therefore, we can't just say that this reaction force is going to be directed along the arm. We have to keep it as its two individual components. Cool. All right. So we have the simplification in here. We have we know our weight here. We know the location of this reaction force. We know the location of this load. The only thing we don't know are these two reaction forces. So let's solve them. What's the first thing that we're going to try and do? Just go for your favorite method of solving statics problems. Sum of forces, some moments, all that kind of stuff. Okay. So which one do you want to do? So which one do you want to do first? Okay, it's up to you. Ready? Go. Solve. Okay. And for anyone who wants to follow along, I'll just kind of start writing stuff here. You'll need all these numbers later on, so I promise this is not just a pedantic exercise in statics. And I'm just erasing the loads so that I have a little bit more space. Everything else will be there. Okay. Yes. Sweet. I like it. Thank you. Although it should be, yeah. The stuff I'm writing now is just saying that the angle of the weight of what's called the counterweight and the force due to gravity are the same as the angle of the arm. Just kind of writing out stuff like that. But in the end, you should get I'm blaming Windows Ink right now because this worked great a month ago. So if anyone who's going down the sum of moments route, you should be getting what's called positive moments from the counterweight and the weight of the arm itself. So if you've gone down the moments route, you should get something like this-ish. So counterweights generate a moment at a sign, which is called at a distance L from the bottom pin times the sine of the angle of the arm. Add that to the moment being generated by the weight of the arm at distance L/2 from the bottom of the arm, and then subtract from that force of the which is called the moment generated by the hydraulic ram at distance about 18.7 feet from the bottom of the arm at an angle theta minus 20 degrees. Be happy with this? Not happy with this? Disagree with this? Okay, we're good. Sweet. So there should only be one unknown in this equation. So what do you get? What do you get for a number for the force of force of the ram. Or if you've gone down another road, what do you got? Should end up, oh yeah, I guess the obvious, it equals 0. So if I file this out, have like 18.7 bar sine minus 20 degrees equals all right. Say again? Yeah?
She was asking 132.
Oh, theta, yeah. It's called theta is whatever the angle between the arm and vertical is. Yeah. I was just using it a lot. So left it as theta. Left it as theta. Okay. Crunch numbers and all that thing should give you something out. What do we got? Say it, say it again. 127. Say again. 329, and the units are pounds. Sweet. Pounds force even. Okay, cool. So we getting something close. We getting something close to that. Give or take how many decimal points we all decided to use. Cool. All right. So that gives us one reaction, and we know its magnitude, we know its direction. So I'm just going to erase this because I have it written up over there. Okay. Okay. So if we're all happy with that, well, I don't know if you're happy with it, but as long as we followed along, we good? Okay. Cool. All right. So if we know the reaction of the ram now, we should be able to get the reactions at the base. In interest of time, I'm not going to worry about that one just yet because I think that all my examples can get by without it. Just going to write down this number off to the side. All right. So after that, let's get back. Okay. So we know the force here, and that should be good to keep us going on. But as I said before, so getting that force is only half of the game now. Your homework may look like may look a little bit like statics, but again, we're trying to give that force some meaning. So once we have that, what do we do with it? And this may look a little bit familiar from last semester or whenever you took statics. Stress, call it a measure of the internal loading that's caused by those forces. Like if I put if I pull on a piece of straw and a piece of steel the same the same amount, they'll affect them differently, right? And it's because of the difference in stress. As far as units go, stress is a force distributed over an area. So this is just units of say force divided by some length squared. So Newton per meter squared is a Pascal. This should be 1 million pascals. My apologies. If we're working in metric, anyhow, in English, you'll see PSI, so pounds per inch squared, or in a weird twist of fate, the kilopound or a kip, just 1,000 pounds. Don't ask me why metric prefixes made their way into the English system, but they did. This also means that you'll see KSI, which is 1,000 pounds per inch squared, or an MSI, which is a million pounds per inch squared. All right, so just some basic nomenclature before we get going. Also, these are most commonly used things for stress. We'll go over what each one is as we go forward. But we're actually going to start with sigma. Sigma was most commonly he used to denote normal stress. So normal stresses are caused by a force acting perpendicular to a face. So if I'm pulling a bar apart, say, so like I have a marker, I'm pulling from either end, I'm creating a normal stress in this marker or in this bar. We can compute it by just taking whatever that force is. These are all what's called equivalent in blocks, right? If I do my statics on each one, it's everything everything's equivalent to the whole bar, right? So I have my force, I have my area, my normal stress is equal to force over area, and my average normal stress anyhow. It could be the actual stress that's acting over the area, but not necessarily. We're going to talk about when it is, when it isn't, what to do about that as the class goes on. I just want to make sure that we're aware of that. So with that in mind, let's jump back to our crane. So again, this is 11,900 pounds. We know we know the force acting here. We know the force acting here. Let's look at this let's look at this hydraulic gram for a moment, though. So if we only look at that, we know the force, we know the force that's acting on it. It's a two-force member. So those are the only forces. That is the only force acting on it. That 127,329 pound force. There we go. So this is the ram. Okay. We know that forces at each end must be parallel to each other and the bar by Newton's third law. They both must be equivalent to each other. So we know the force. Just check something. 10.5 inches. This has a diameter of 10.5 inches. So how do I find the stress in the normal stress in the hydraulic ram?
Find the cross-sectional area.
Okay, which is?
5.25.
Okay, so we can say more conceptually something like this, right? Okay. Nice job with what's called the math all on the fly, though. I really appreciate that. Nice. So we can work with that, and that ends up being, it should be pretty close. It should be like maybe like 6. My guess is 6 something.
We converted to feet.
Do you have to? What units of the stress?
Force per area found PSI.
Yeah, PSI will work. 7.22 what? Feet squared?
If it was in inches, it would be 86.5.
Okay. All right, so that's in foot squared, and 86.59 is inches squared. Okay, cool. One day I'm going to actually be able to not have my sleeves hit this. Okay, so 86.59 inches squared. My apologies for doubting you before. All right, so we have an area, we got a force. What's the stress?
1470.5.
Okay. So 1470.5 psi. Okay, I can believe that. Did anyone get another number? Did anyone get another number? You happy with that one? Cool. All right. So yeah, that's pretty much it for normal stress. It's relatively straightforward process. You all happy with that? Cool. All right. So next switch call. So the next kind of stress that we're going to be talking about is shear stress. So this is the one that's normally denoted by a tau. Two nice little simplifications for this are either single shear or double shear. It's pretty much exactly what it sounds like. Which call instead of transmitting force through a single bar, so like I have my marker, I'm pulling on each side. Now I'm transmitting forces kind of sideways. So here, instead of the force acting perpendicular to the cross section, here force is acting parallel to a cross section. So the cross sectional area that is going to be of interest in computing a shear stress is the cross section that's parallel to the force, as opposed to a normal stress where the cross section that we care about is the cross section that's perpendicular to the force. All right. In single shear, that force the force that's pulling here is being transmitted through one member here. In double, which call it in double shear, it's being transmitted through two. So you can do your statics on Charles. You can do your statics on this and say, hey, the force is going to be half in this situation than it is here, etc., 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 etc. So you can guess at the implications and here. It's just some terminology that you'll be hearing as time goes on. So how do we just again, how do we compute it? This is a single shear example, so we have forces acting on each side. If we look at the internal forces, so we cut this bolt in half along the plane E, so we can replace. So you see we can replace it with a statically equivalent model, right? And we can get an internal force along this plane. So that plane, if I backed up a slide, would be right here. So that'd be at the joint between those two boards that I'm pulling on. All right. So if I know the load at that point along that plane, I can figure out how the cross-sectional area that is parallel to that force, and I can get my shear stress. Again, this is an average shear stress. You're going to be hearing that word a lot. It's an average. It's not necessarily uniform across the cross section. We're going to be talking about that more later on. So let's look at, again, not the ram, but the arm this time. So, oh, it won't let me do it. That's annoying. Okay, so we're going to do this on a on this slide. Okay, this is 11,900. All right, so let's look at let's first look at the shear stress in this guy. How would I go about finding the shear stress in that member? What do I need? If normal stress was me trying to pull this marker apart straight out, and shear stress is kind of going across it, what forces do I need in order for shear stress to occur here? How do I find out the amount of shear stress in that member, if there is any?
Would it have to be a pivot?
Okay, it could be. So we have a pivot there, we have a pivot there. We have force, we have force. Stresses are internal though, right? So I could have a stress anywhere in here. But this force, the forces acting on this ram are parallel to it, correct? So as opposed to like here, there's no force going across it. There's no force perpendicular to the ram, correct? And that's what creates a shear stress. So is there any shear stress in that ram? Correct, because there's no shear force. If I wrote out a shear and bending moment diagram like you did in statics, you'd find there's no shear force because there's no force perpendicular to the ram. However, what about here? Do I have any force that's perpendicular to the arm?
Yeah.
Yes. So Let's go to the very end. I know that we're almost out of time. I have a 20,000 pound counterweight hanging there. What's the component of that will create a shearing force? Or rather, I'm just going to work it out because we are out of time. So have 20,000 pounds going straight down. It's at an angle, it's an angle of theta equals 32 degrees, I think, did I say? 37 degrees? Oh, hey, 32. Let's go 32 degrees from the vertical. So if I take the 20,000 sine that, I get my component of force perpendicular to the arm, right? So that gives me half. So that gives me half of my shear force equation. So 20,000 sine 32. Okay, and the cross sectional area is based on it's 39 and a half, 39 and a half inches. What's called the cross sectional area is just pi d squared over 4. And that's your shear stress. If we assume that the arms has a circular cross section. Are there any questions on normal stress and shear stress? Should be at least a little bit familiar from last semester, I think. But that's kind of where we're getting started. All right. Thanks for stopping by. I'll see you on Thursday.
Wait, can I tell you something?
Sure.
I don't